Namaskar my dear friends. So let us design an LED driver that will be for automotive application. Basically these kind of LED drivers can be used for your interior LED drivers or exterior applications like side indicators or something like that. So why do we do this kind of like application circuits? What is the main agenda for these particular applications, and the concepts are basically it will help you to understand what is hardware design engineers, like how you can become a very good hardware design engineer or electrical design engineers or electronics design engineers. So what is the thing that we do basically in the first statement or first place is basically we try to identify what is the problem. Okay, there will be a problem statement or the challenge that will be there with us. Either you join any industry, whether it is industrial solutions or whether it is automotive solutions or medical grades or like aerospace, defense, any of the industries you join, you will be having some challenge or some problems. Okay, once we do that, then we try to explore the concept, like what is the methods or what are the different solutions that we can look for, and then we try to find out a optimal solution. Okay, so once we understand what is the exact solution, once we have identified them, then we go for solution implementation. Once we implement that, basically we design the circuits and we go for testing and verification. Once we test and verify them, then we can go for validation so that it can go into the market. Okay, so our aim would be to understand what is my automotive constant current LED driver and how it can be made very easy to implement for our automotive applications. Okay, so through one example we will understand this particular concept. The example that we will be taking using one of the IC, that will be BD18347 AEFV-M. Okay, so this is a particular LED driver which can give you up to like a 40 volt and 150 milliamperes of current per channel, and it has 4 channels. Okay, so there are 4 channels that can give you the output. Okay, so let's get into the IC itself. Through this IC explanation, you will understand what is basically electronics design engineering and how you can apply your like learnings and concepts to design this particular LED driver. Okay, so first of all, if you see the data sheet, you will understand this is a 40 volt 150 milliamperes maximum current and with 4 channels of constant current LED driver. Okay, basically if you see some key specifications are, then key specifications are given as maximum input voltage that it can take is up to 20 volt. It can give you current up to 150 milliamperes per channel, and output accuracy is going to give you 5%, and relative channel accuracy is also 5%, and the operating temperature range for this particular IC is going to be up to 125 degrees centigrade and as low as minus 40 degrees centigrade. Okay, the basically if you talk about package of this particular IC, then it is going to be HTSSOP 16 package. Okay, and it has other functionalities also, features and all we will see, like it has LED open detection, short circuit protection, LED short detection, all these things are there with this particular IC. So what would be the outcome of this particular session is, let me first tell you very clearly. We will design the circuit like this. We will have our power supply section, which we have designed it, let's say from 48 volt battery or let's say 24 volt battery, which is there in automotive engineering or automotives. Okay, so from there we can get a 12 volt through some switching regulator of automotive grade, and from this 12 volt we can get a 5 volt also, which is going to be linear regulator. Okay, and this 12 volt and 5 volt will be utilized to supply the voltage for this particular LED driver. Okay, so LED driver complete like implementation you will be having with all the output channels and LEDs. So how we are going to design all these particular values? First of all, we will try to understand the design and details from the data sheet, and then we'll get into this particular value implementation or this particular schematic design. Okay, so directly explaining this particular circuit may not help you. However, you can keep this screenshot for your understanding for now. Anyway, I will be explaining this thing in detail at the later stage. Okay, So first, let us get into the data sheet and product page also, so that you will have an understanding like what is basically this particular LED driver. So if I open this particular web page of ROM Semiconductor, from where I have taken this particular constant current LED driver is BD18347 AEFV-M. Okay, so if you see, they have like it is recommended for new design, that is given here. They have some minimum and maximum voltage like input, which is 5.5 volt and 20 volt. Current per channel is 150 milliamperes. Number of outputs are 4. It has a dimming option, which can be through PWM, and all other things are there. It has common standard, which is AEC Q100, which is automotive grade. Okay, some of other features are, if you can see, it has qualified for AEC Q100 as I told you. Then it has functional safety supportive for automotive products as well. It has energy sharing control, it has PWM dimming, it has license lamp mode, it has LED open detection, it has output short circuit protection, as well as over voltage mute function is there. Disable LED open detection is also there. We have reduced voltage functionalities and LED failure input and output functions also. Okay, using one of the P bus, basically it is power bus, something is there which can give you the understanding of whether the IC is in failure fault mode or not, right? Okay, so and this is the complete data sheet that you can see. So it is of around 38 pages. We are not going to explain each one of them. However, in the presentation I have put almost everything. But before moving to that, what I will do is, let's get into the data sheet from presentation that I have taken. Okay, okay, so we have already done the features. Now get into the application. So as you can see, it can be utilized for your LED exterior lamps. Exterior means like automotive exterior lamps means like you have the car and the exteriors are like rear lamps, or like license lamps or indicators or something like that. It has some like driver position lamps or fog lamps or something like that. If you talk about interior lamps, there are basically air conditioner lamps and interior lamps, and cluster lightings is also possible. So using this particular IC, BD18347, you are going to have the application in these areas. Okay, there are various other ICs also. I am just going to explain you using this IC the concept of designing this circuit. Okay, I'm not recommending or you, or maybe like not forcing you to utilize this particular IC for your application. Once you understand this, then you may be able to extrapolate or like extend your concept of design with other ICs as well, or your suitable ICs as well. Okay, coming back to the typical application very beginning, the design is very simple. These are the outputs. As you can see, we have like a capacitor on each of the output, so 4 capacitors, and these are the LEDs in series. Okay, so this is how the design is. That is your outputs. All the output currents can be set by set resistors, which is R set 1, R set 2, R set 3, R set 4, using this set 4 set pins. Okay, so this is going to set the output current of each channels. If you want them to put equal amount of current in each of the channels, you can put the same values of resistors in each of the channel here. Otherwise you can set different currents as well, but make sure the output current that is set is up to 150 milliamperes maximum. Okay, it should not be more than that. I'll give you the design process, like what should be the value for what current. Okay, coming back to M set value, like mode setting. So there are two mode setting, mode setting 1, mode setting 2, and this is the like indicator for fault or something like that. Okay, so it is actually open drain output pin, so you have to keep one let's say this is my 3v3 or 5 volt or something, and then it can be like pull up and going to the microcontroller or maybe some LED for indication. Okay, coming back to CRT and disk pins, so they are basically PWM pins. Okay, so PWM dimming pin or something like that, so they are going to control based on the RC value. So this is capacitor and this is resistor values. Okay, coming back to the input, so this is my, let's say, battery voltage. So they here they are shown into like PWM mode as well as DC input mode. Okay, so if you are going to have PWM mode, you give it to through an external resistor. So this external resistor is going to like limit the currents into the V in resistor, and this is your input voltage, okay, of the IC. and these are the input capacitors C in 1, C in CV in 1, CV in 2, and we have one here put like MOVs. If you want you can put it, otherwise there is no need if your input is quite clean. Okay, and this is how this complete typical circuit is there. Okay, so this will be the typical circuit that is given in the datasheet itself. However, we will try to understand each and every pin functionalities and their definitions one by one. Okay, this is how you understand a complete design. Okay, so if we talk about a pin configuration, it is having a 16 pin IC with one exposed pad as well. Okay, so as you can see, we have V in race, a resistor, V in and P bus on all these things. So we'll see the pin configuration here. So if you talk about V in race, then it is going to be energy sharing external resistor connection. Then this is your supply voltage input, and this is P bus is going to be your output for fault flag or input to disable output current. Okay. Then this is CR timer setting. This is CR timer setting for CRT and disk. Both are there. So this will be having one capacitor and this will be having one resistor to that. Okay. We have mode setting 1, we have output setting output current setting pins. These 4 pins are there. We have mode setting 2, and then we have ground pin, and we have current output 4 pins are there, and we have exposed pad that must be connected to the ground again. So this and this both should be tied together to ground. Okay, so this is as simple as that. Coming back to the block diagram of this particular IC, once we talk about this, what is there is as you can see, we have external energy store like sharing pin, which is V in RIS, and then we have input supply pin. So this is energy sharing control for that. Okay, coming back to this fault pin is there, P bus. We have mode settings, mode setting 1 and mode setting 2 based on the control logic that is there, and we have CR timer. For this is going to be connected through like one capacitor, and this will be connected through a resistor. Okay, so like that they are going to control my PWM dimming functionalities. Okay, so these MOSFETs are going to switch on, switch off based on the duty cycle and the frequency that is given at this particular PWM, and this is how it will be giving you the dimming controls. Current setting is going to be through the set pins, as you can see here, and these are the outputs that is going to drive my LEDs. Okay, so this is very simple block diagram. Now coming back to the some of the like parameters of this particular IC, if we talk, so whenever you take any IC, you have to go ahead with maximum like ratings, that is called absolute maximum rating. So absolute maximum rating, you have supply voltage maximum up to 40 volt rating. Okay, but the recommendation was up to 20 volt only, so you have to understand that you should not give more than 20 volt at the supply input. Okay, coming back to supply voltage V in RIS, that also is going to be like plus minus 40 volt, but it should be less than V in. Okay, then we have other voltage as well. You can see V in raise, then CRT, V CRT, V disk, V like mode settings, then output voltages are there, which is going to be maximum of minus 20 volt to V in plus. Okay, we have P bus, which is going to take up to 20 volt, and we have storage temperature up to 150 degrees centigrade, and the maximum junction temperature is 150 degrees centigrade. Okay, good. So this was absolute maximum rating, but we should not see this as a recommended like parameters. The recommended values will be next. So let us talk about this recommended values. So generally we have to have this thing only in our mind. So V in must be like typically 13 volt, or maximum is 20 volt. So we are going to give like 12 volt input at the like supply input. We have output current, each channel is maximum 150 milliamperes, but we have designed for like let's say 75 milliamperes or 100 milliamperes, so that it is more than enough for our automotive design. We have CR timer frequency is 750 kilohertz. Okay, and we have PWM pulse width, minimum it will be 100 microseconds, so you cannot have lesser than this pulse width, otherwise it will be a problem. So anyway, we have kept around 300 microseconds, something like that. Okay, operating temperature is 125 degrees centigrade only. Absolute is actually 150, but you should not make the IC to reach more than 125 degree. Some of the like values for each of the pins that is given in this range. So you have to have input capacitor minimum 1 microfarad. So basically we try to take around 22 microfarad or 10 microfarad. Okay, and we have one more capacitor requirement, which is 0.047. So generally we take 0.1 microfarad. Okay, then we have four output capacitors at the LED anode pins, and those are going to be zero point 0.01 microfarad to 0.47 microfarad. This also we have generalized it to zero point 0.1 microfarad. Okay, coming back to CRT CR timer capacitor, so that also we have taken like 0.1 microfarad. This is the range of those. Then CR timer resistor is going to be like minus 0.1 ohm to sorry 0.1 kilo ohm to 50 kilo ohms. So that also we have taken some values. I don't remember this. Let me just see once. That is taken as 3.6 kilo ohm. Okay. Coming back to like the R set pins for current setting output. So the minimum should be 12 kilo ohm to maximum 36 kilo ohm. Okay, so based on the formula that we will be deciding, and we can calculate based on the I output required what should be my R setting resistors value. Coming back to some of the like very important curves that we have to have in our mind. So if you increase your Vin, okay, then your output current actually increases little. So as you can see, up to around 6 volt or something, the current has increased to like 4 milliamperes. Okay, so no current output circuit current in normal mode. Okay, so this is how it is going to work. Okay, and based on the temperatures it is actually varying. So as you can see, if it is 125 degree centigrade, the current is going to be close to 4.5 milliamperes. Okay, so that is I V in. Okay, so the current into your V in pin will be this much. Okay, basically the circuit current in normal mode versus supply voltage is this particular things. Coming back to current setting resistor, so as you can see, let's say you want to set it for 80 milliamperes, then you have to go ahead with slightly more than 22 kilo ohm. Okay, if you want to set it for 100 kilo ohm, then you have to go 100 milliamperes, then you have to go ahead with 18 kilo ohms of resistor. Okay, if you are say going to set for 60 milliamperes, then you have to go for 30 kilo ohms. Okay, so this is how it is going to work. So you should not go ahead below, I think, this 12 kilo ohm. Okay, which is this range, and above 36 kilo ohm, which is this range. Okay, so as you can see, you cannot set less than 50 milliamperes and more than 150 milliamperes. So this is how the current setting resistors are going to help you with this particular curves. Coming back to some of the values that is there. So as you can see, for 36 kilo ohm it is set to like 50 milliamperes, 18 kilo ohm it is set to 100 milliamperes, and for 12 kilo ohm it is set to 150 milliamperes. Okay, so this is output current that is going to be there. Using this graph you can see and set your values. Otherwise there is a formula also for other values. If you want to set, you can set this using that formula, and with that R set values will be calculated. However, this is more than enough. I have myself used, I think, 24 kilo ohm for 75 milliamperes of current. Hope you have a good understanding till now. Now let us go into the design process. Okay, so design process, as I told you very clearly, what should be the I out. So let's say I out values I want to set it for 100 milliampere. Then what will be the formula? K set by R set. So R set we have to calculate for I out values. So I out values, let's say 100 milliampere if I am going to do, then what will happen? 1800 by 100 milliampere is going to give you 18 kilo ohm. Okay, let us say you want to set it for 75, then 1800 by 75 milliampere, then it will come up as how much? 24 kilo ohm. So R set values will become 24 kilo ohm. If you want to set the same current to each of the channel, then you have to use 24 kilo ohm to each of the channel. Okay, now very important thing is what should be the minimum V in required. That should be input voltage that will be required at the V in. Okay, so that we have to understand first. So what should be that is how many LEDs that you are using. So let us say we are going to use 3 LEDs multiplied by each of the LEDs forward voltage drop. So let us say each of them are having 3 volt drop. just to be very like nominal, or 3.2 also it comes sometimes it comes 2.8 volt. So we'll just take 3 volt for simple calculation. Then we have VDR, which is going to be like dropout voltage in V in resistors, and plus V in V resistor into I out total. Okay, so I out X total is going to be 75 multiplied by 4. Okay, so 75 multiplied by 4 into input resistor, let us say 100 is there, or divided by 4 because they are in parallel, let's say. So like that it will be there, plus some VD resistor, VDR, you can see voltage drop across the resistor will be voltage drop across these resistors. Okay, these resistors. So let us say that is dropped like around 0.5 volt or something. So using this, like 3 3s are 9, plus some current is going, some voltage is going to come. So my V input must be more than this voltage. Your common understanding should be like this, that whatever the values that is coming to this, your input voltage should be more than that. Okay, now let us see some other parameters. So how we are going to set the output current setting? So we have already told you, R set value you have to put it through the set X pin to set the like output current. Okay, coming back to like this is how you are going to get your I output in each of the channel by this by setting the resistor value at the set pin. Okay, and this is how the LEDs will be connected. The I out total will be coming up as I out 1 plus 2 plus 3 plus 4. So this is how total current will be there, and this much will be required at the input supply also. Okay, coming back to next is PWM dimming operation. So PWM dimming operation can be of like different kinds. So either you can supply through here itself through one MOSFET switch or something, so that you can switch on switch off at a particular frequency, and this is how input will be like taking the PWM input itself, and this is how your output will be dimming. Okay, so PWM you already know that it has a pulse width something like that. So on time, off time, so this is T on and this is T off, and this is your total T time. Okay, so duty cycle is nothing but T on time divided by total time T, and this is how your duty cycle will be there, which can be like let's say 75%, sometimes we keep 50%. If half is on, half time is it is off. Okay, good. So this is how a PWM operation will be there, and this CCRT and RCRT will be actually charging the like timer, CR timer, and this is how it is going to help you in your dimming concept. So this is a triangular wave that is going to come. If you can see very clearly in the data set itself, it is shown here. So this was my frequency of FPWM, which is going to be 1 by T, that is total time. And what happens is at the rising time, this triangular pulse rising time, what will happen? It will give you like the CRT is sorry, the CRT waveform is going to be charging, and at this time when it is going to down, that time you will be getting your output. Okay, so this time the LED will be off, and this time you will be getting on time. Okay, so the output current I out X will be like available when it is coming down, when it is coming down, when it is coming down. Okay, and while charging it is the output will be 0. Okay, so that time it will be switch off. Coming back to like PWM dimming using external signal is also possible. So instead of giving the voltage supply here in PWM form, you can give supply continuously, and through some microcontroller or something you can give like one PWM pulse at the CRT pin. Okay, so this will be little easier for you, because this is going to be very independent of this particular input voltage, and it will be little bit easy using software. You can control your like PWM dimming of the output currents. Okay, so this is another method of this. So these are the like different methods that we do for our PWM dimming or current setting and all these things. Coming back to other parameters, going to like short detection. So if you talk about short detection, what happens is basically the R set pin that we have like I set pin has been used for using resistor setting. So what happens is this particular whenever it sees a short circuit, okay, so in that case what happens is this particular current setting resistor will be short circuited to ground, means it will see a very huge amount of current, and at that time what will happen is my P bus will be pulled down. Okay, and if it is pulled down, then what will happen, it is going to indicate a fault. So basically in the circuit design we keep it pulled up. Okay, let's say like 3V3 we are keeping, or 5 volt, and whenever there will be a fault at any place, it will be pulled down, that will become 0, and this is how we can recognize the IC is in fault condition. Okay, so that the IC is not damaged. Similar to that, we have LED open detection. That time also our V out pin will be actually voltage rising, and in that case you can see the output voltage is more than like V in raise minus around 50 millivolt, and in that case you can see that my fault detection pin is again because of my P bus is going to be pulled low. Good. Coming back to the other parameters, if you can see LED connections, so LED has different kinds of connections. This is very simple string in series, so 3 LEDs like 1, 2, 3, and with one capacitor to the ground from the anode of the LED. So this is simple connection that is there. Another connection can be like a parallel connection, like more strings of LEDs will be there for better brightness. Let us say we have I output enough, and like let's say 75 milliampere we are keeping, so in each of them like 25 milliampere will be shared. Okay, so this is how these three like strings of LEDs, or maybe more LEDs strings can be taken. Another one is matrix kind of LED, where like all the anodes will be connected, so basically only once like a row of LEDs will be connected together, and this is how another connection is there. Okay, so what you have to do is, there will be a capacitor that is connected from the anode of the LED to the ground at the output pin, that must be connected with like 0.1 microfarad or little higher value, as I told you. Okay, to avoid some erroneous output. Okay, so this is very simple design. As you can see, you have the input, we have CRT pin with a PWM and DC input, and we have current setting resistors, and this is the output LEDs. So it is very simple as that. You don't have to go ahead with or get into a lot of like mode setting, or even P bus is not needed. This is very simple design to keep your design going on. Okay, let us now talk about some of the applications that is given in the datasheet itself. So very first application that was given is I out X is set to 75 milliampere per channel in license mode. License mode means basically both the MSET pin will be left out open, like left floating, there is no issues at all. And PWM duty is set to 10%, with PWM width is going to be 334 microsecond, and PWM frequency is 300 Hertz. Okay, so here one MOSFET will be used, okay, which will be doing that job. Here also one MOSFET will be used to switch on or switch off the input voltage using the VBAT. Okay, so VBAT is nothing but the supply voltage that is coming from either battery, or it can come from some power supply regulated output. Okay, and these are the diodes that is going to like give you the like input protection, and this is the like ESD protection, something like that, which is going to be a MOVs. And we have, let us say this is my 10 microfarad and this is my 0.1 microfarad capacitor. Similar to that, this is my 0.1 microfarad capacitor, and this is, let's say like 4.7 kilo ohm or something, and we have all 0.1 microfarad capacitor, C out 4, 3, 2, 1, everyone. Okay, and these are the LEDs that is chosen. Already I have taught you in our previous session. You can see automotive LED selection. Okay, so I have given you an like a previous video which will give you an understanding of how we can like set the or how we can select automotive LEDs for our application for interior design or exterior design or everything. Okay, so automotive chip LED selection that we have already done. So those LEDs you can utilize here. Either they can be of like a yellow colors or red color or even green color or like blue color or some magenta color. Any colors are there with different current ratings also. Let us say some of them require 20 milliamperes of current with low brightness. Some of them may require, you know, like 50 milliamperes of current. If very high brightness you need, then you can go ahead as high as, you know, like 80 milliamperes or 120 milliamperes even. Okay, but make sure the LED voltage drop should not exceed more than the input voltage. Okay, and I setting is there, which is set to 75 milliamperes. In that case, all these I set values will R set values will be 24 kilo that we have already calculated. So this was the complete design. They have given you the data sheet also, like recommended part list. So if you want, you can utilize these. Otherwise, you can use other parts also similar to these. Okay. Anyway, coming back to the other design, that's design number 2. So they have also given you, you know, like I set values at 100 milliamperes. In that case, R set value will be a little bit, you know, like lower, which will be going to be, I think, 18 kilo ohm. Okay, so 1800 by I set is 100, so this is going to be, this is milliamperes, it is going to be 18 kilo ohm. So all the R set values will be 18 kilo ohm for this particular I output current. Okay, and rest all are same. It is going to be a stop application with mode setting as low. In that case, you have to, you know, like ground both the mode pins, that is mode setting 1 and mode setting 2. That is the only change that you will see. With same PWM duty cycle and pulse width with PWM frequencies are same, so these values remains same as previous design. Okay, so hope you have a good understanding of how to understand the, you know, like given design application in the data sheet itself, and we can leverage this particular, you know, like inputs or particular solutions or concepts to our exact design that we are going to have in our application. And this is the complete part list for the second design. Coming back to the third design that is given in the data sheet, which again 100 milliamperes per channel. So all these R set values will be set to 18 kilo ohm, that you know, right? Coming back to have a, you know, like a PWM control from external signals. So what is going to happen is, either you can do one thing, you can give external PWM signal to CRT pin, that is one method. Okay, second method is each of the, you know, like set pin, what you have to do is either you can switch off or switch on the R set value itself. So once you switch off this R set values pin, like I set pin, then what happens, let us say it is going to come up as PWM signal. So what will happen when it is on, when it is high, then this MOSFET will be switched on, and this is how the current will be set in that channel. Once the current is set in that channel, then I output current will be available. Okay, so I out 1 will be available. Okay, and this is how the LED will be glowing. So this LED will be glowing, this particular LED will be glowing. Now let us say when it is, you know, like off cycle, like on cycle you understood, off cycle, then R set value will be floating, like this I set pin will be floating actually, because MOSFET Q1 is off. So in that case I out 1 will not be coming, and this is how the LED will become off. So this is how it is going to be having a dimming function. Similar, you know, like concept is being used in R set 2, R set 3, R set 4, using these Q1, Q2, Q3, Q4 MOSFETs to switch off the current setting and switch on the current setting based on the PWM input coming from the microcontroller. So basically you have to have a microcontroller with 4 PWMs that is coming up to set the current settings as well as current setting duties. Okay, and this is how you are going to have dimming control in this. So the very beautifully they have shown here in the figure is, this is the highest duty cycle, so this will be, you know, like giving you a brighter signal. Compared to this one, this will be little dimmer, this is more dimmer, and this is the least, you know, like a very dim light that will be coming, because the high duty cycle is very small. Okay, rest others are almost same. So hope you have a good understanding of this particular IC, and also a good understanding of how to get into the, you know, like PWM PWM dimmings and LED driver design. Let's get into our design that we have designed it for you. So this is the design implementation that we did. So we have input voltage of 24 volt or even 48 volt, it can work. It can directly give if you for 12 volt, then also it will work, but I have designed it for 48 volt. So from 48 volt I am going to step down using a switching regulator. Switching regulator will give you 12 volt. Okay, so this 12 volt is again taken into here, and this 12 volt is going to get this particular automotive linear regulator, which is TLV766Q1, and going to give you 5 volt output with 500 milliamperes rating. Okay, and this is going to give you around 1.1 milliampere 1.1 amperes of rating, that is 1100 milliamperes of rating. This is the IC which is LT8619. So okay, so power supply section is complete. Coming back to the LED driver section. So in LED driver section what I have done is the current setting is set to 24 kilo ohm. It means it is I out is set to 75 milliamperes. Okay, maximum is 150. So 75 milliamperes I have set the current. Coming back to the LEDs, so same way LEDs connections I did like D4, D5, D6 using the LEDs that I have showed in the previous section. Okay, so those automotive LEDs of your own color choice, or any desired color that you want, you can put down here. Those LEDs will be fine. So similar to that, all the 4 output channels has been connected. Coming back to the mode setting, so mode setting I have put it grounded, so that there is no mode setting used. Okay, or I want it to be like a stop when there is a fault. So, okay, when there is low. Coming back to CRT pin and disc pin, so there I have used 0.1 microfarad and 3.6 kilo ohm. Okay, to have the PWM dimming. Coming back to this P bus, that is power output bus, so there what I have done is this is anyway going to have a fault indications. In that case I have pulled it up using the 5 volt that is there in our previous power supply section, and at the same time this is going to go to my MCU IO with 5 volt tolerant pin. Okay, now the same thing what it has done is this particular pin is connected to LED. Okay, so what is going to happen if there is no fault, then this green LED will be always glowing. Okay, and when fault happens, then what happens is basically P bus is pulled down. In that case this particular LED will be switched off. So once it goes off, then I will see the IC is in fault condition, or it is in a problem situation. Okay, alright, coming back to the input section. So input section what I have done is, if you have a PWM signal here, okay, that you can supply through this, and this MOSFET will help you to pass this particular PWM signal to the input, and this is how it is going to give you the dimming functionalities, right? So this can be controlled through the microcontroller. At the same time, if you want to give directly DC input, then this directly DC input will be coming as like enable signal. Okay, enable signal, that is coming as DC in from the microcontroller, and this is going to switch on switch off, or maybe gate driver, this is going to switch on switch off this particular gate of the MOSFET, and this 12 volt input will be coming back here to be 12V in, and this is how it is going to supply through the input supply. Okay, so at the input I have used 10 microfarad and 0.1 microfarad capacitors. 10 microfarad capacitor you can use 25 volt rating or 35 volt rating, and this 0.1 microfarad with 50 volt rating. Okay, rest all 1.1 microfarad capacitors with 50 volt rating should be fine. So hope you have a good understanding of this particular implementation. If you want to have some extra understanding of any particular design, or any other method of designing this particular IC, or maybe if you want to have some other automotive LED driver application using some other number of channels, let's say 8 channels or 12 channels or 16 channels or even 24 channels. So we will be coming up with again one more very good workshop with 24 channel LED driver ICs, which will be very high end IC from ROM Semiconductor itself. We will take an example so that you have a good understanding of how to design some backlight driver for automotive LED clusters. Okay, or automotive cluster design, how we can design using 24 channel LED drivers. Good. Some of the parts that if you want to take up for your LEDs that to be used in this particular design here, so you can take up these LEDs. These are the part numbers that is there, which is automotive industry 0603 size of low brightness reflector type white LEDs. This is blue chip LED with low current emission, and this is like high brightness LED. So any of these LEDs, or like some other LEDs also, if you want to use, I have already given you a training session in the last session, so you can use using those LEDs. Okay, so thank you so much. If you do have any questions, please put down your queries in the comment box, and we shall be able to come up with the like proper answers. And if you have a particular requirement or particular situations where you are facing LED driver design challenge, then we can always help you out in that respect. Thank you so much.